think that there's a lot of conflict with, the words in this title, that people have a lot of different views on design, different ideas about how you balance complexity and abstraction, and definitely about types. We live in a world dominated by JavaScript and dynamically typed languages, and we have to compete with that and really make the case for what types buy you, and what you can do in typed languages that you can't do, or what you can do in strongly statically typed languages that you can't do in dynamically typed languages, because it's not just about method dispatch and dynamic binding or message passing. That types can buy you a lot more than than just syntax. So a little overview of what I'm going to cover today. So the first I want to make the case against what I call interface pollution, which is something that is particularly pervasive in Scala, since we have wonderful traits at our disposal, but they're a little bit of a catch-22 because it's really easy to add convenience methods to your interfaces, and that can really hurt the evolvability of designs in the long run. And so I want to I have a running example that I'm going to go through that to really try and make clear the different ways that I think this interface pollution happens, and it's generally well-meaning, but really show the ways that it breaks down and fails. And then as a proposed solution, I want to show something that is rather unique to Scala, which is this idea of family polymorphism, that you don't have to deal with strictly uniform class hierarchies, that using particular combinations of Scala's type system that might seem esoteric at first, they come together in a really nice way to let you extend a set of types together to effectively have loosely coupled interfaces with tightly coupled implementations. And it leads to really nice results that are clear and sound, which is really, really key, that the compiler can thoroughly check your code. And it removes a lot of assumptions out of your code, allowing it to be simpler and well-performing. And that will lead into, I don't really like the word design pattern, but for lack of a better, what I call the cupcake pattern, which is, many of you may be familiar with the cake pattern, and this is what I call the cupcake pattern is a play on that favors using smaller cakes composed together rather than these kind of monolithic abstractions with lots of types that can become unwieldy. And then we're gonna, and so I want to be really concrete at the beginning of the talk and really give a motivating example for why this stuff is useful and why you even would bother knowing that these things exist. And because there's an energy barrier sort of with complexity. I'm essentially advocating that you add a little bit of complexity to the types in your code to reduce the long-term complexity, and in particular combinatorial complexity, where with every new module, every new feature you add, you end up multiplying the amount of work you have to do by the number of existing modules. And this is something that I found to be particularly pathological with certain Scala designs, where things kind of run out of control really quickly if you don't really deliberately manage combinatorial complexity. And then lastly, I'd like to end with a little bit of a discussion and Q&A generally, but also hear what others' experiences have been with pushing Scala's type system to its limits. So with that, let's start with talking about interface pollution. And so the running example that I want to use for this is a simple abstraction, which is the idea of a number. get about as simple an abstraction as you can get, and yet it's deceptively difficult. Programming languages have a difficult time abstracting over numbers. That we all have our primitive ints and doubles, but how do you effectively model mathematical types? So let's say that this is the abstraction we want. We want the ability to add two numbers. And now how are we going to go about this? You say, well, we need to implement our abstraction, so we want a 64-bit double implementation, but how do we go about actually adding those two numbers? We've got a subtype here that we're adding types of some base type that has no other methods. So there's not a clear way to actually add these things. One way is with a downcast, of course. You can pattern match against the specific type that you're working with. But of course that's completely not sound, and you would never do that. Downcasts are evil. So what you probably would find yourself doing is going back up into the base class and add yourself a two-double method there. Now you implement that, and this is sort of classic OO design, right? And you add your two doubles, and that works great for one case. But what happens when you have another case? So now we want to do it for 64-bit integers. That's also a number. First of all, you now are mixing the implementation for your long implementation with your double implementation. So you're forced to provide a conversion, but that's not so bad. But again, how are you actually going to add these things? Because you're going up against the base class again. And what you probably will do is go back to the base class and add a conversion for a long. And I'm sure many of you have done this lots of different times. I know I'm guilty of it as well. And the core, I think that we accept that you can't really have pure abstractions. That you're always going to tie your abstractions to some particular implementation, and I think that's just accepted as part of the course. But I don't think it's actually necessary, and that's one of the great benefits that Scala enables, and we'll get into the different ways how. And so, in that vein, we've got, this is what traits are for, right? You can provide some standard implementation, and is it that bad an assumption to say, hey, I want my numbers to be convertible to doubles or to longs? But it might be. The whole point of an abstraction is not to tie yourself to those assumptions. So if you want to represent numbers as expressions of numbers, potentially with some irrational numbers, well, yeah, you could coerce it to a double, but you're losing something there. And furthermore, you're by putting these conversions in your base interface, you're encouraging people to use them, and it's going to be difficult to compose your code in the long run. So, what really are the consequences of designs like this? And again, I recognize this is a bit of a trite example because it doesn't look that bad with long, too long and too double, but it's not. I'm sure you can imagine more realistic cases you may have faced with your work where you add things that you think, hey, in my particular case, that's no big deal, and it comes back to bite you later. So, the problems are that the implementation details are leaking into the interface. That to long and to double, those were implementation details, and they bubbled up to the interface to make the object model work. And really those implementation details constrain the interface ultimately. Now, the only things you can represent, you can use your number abstraction for are things that are convertible to long and to double. And more generally, any kind of assumptions or constraining your interface, ideally we want to keep it nice and simple and assumption free. And another just an equally large problem is that the implementation details leak into each other, which is the fact that when we went to implement int64, we had to implement the abstract member that was required for float64. And so every time with each new case that you want to implement, this is how you get that combinatorial complexity. And it's simple with conversions, but as you get into more taxing abstract members, the problem can get out of hand quickly. And you tend to just throw up your hands and give up on having useful abstractions or really general abstractions. And again, the interfaces are convolved with the implementations. That it's a classic idiom, right? That keep your interfaces separate from implementations. Here we have tightly coupled interfaces that are tightly coupled with their implementations, and then the implementations are loosely coupled with themselves because they have to handle every type of number. And so I consider these design errors that are caught at growth time. And again, numbers are a simple case, but they're a useful case because they're easy to grasp. And something that's an error that's caught as you're trying to evolve and expand your system, in my opinion, is kind of the most pathological kind of errors. That compile time errors are great, hey, you catch those, runtime errors suck, but something that you don't find out until you have a deeply developed system that now you need to rapidly and reliably evolve, that's a really bad spot to be. So avoiding it is really desirable and worth the effort. So we really want here is to defer. So abstract methods defer an implementation, right? Say, hey, I'm gonna declare that these methods exist, but I'm not gonna say what they do. What we'd really like to do, how might we actually defer the declaration itself? Ultimately, maybe you do need a conversion to double, but do you need that everywhere? Can you defer that declaration to just the scope where it's needed without sacrificing the abstraction and sort of the general nature of the interface? So one approach, which is really the generic Java approach taken by JScience, which is an interesting library that models numbers, is to use these kind of cyclic type parameters, where, hey, we've got a ring here that's parameterized with itself, or with some subtype of itself. And so now your addition method there always adds and returns sort of the same type of thing. And this allows you to implement your float64 as a ring of float64s of itself. This means you're only adding the same type of thing that you have. So nice and simple, no pattern matching, no downcasting, because you're not working with the general case there. So that's one approach. But it tends to lead to explosive boilerplate and is generally awful to work with, and so bad that people don't work with it. And you can see that if you try and sort of, a really important part of abstractions, you have to be able to compose them, otherwise you're not getting anything, right? That in order to make that energy barrier worth it, you have to get to some deeper simplicity, or you're really not getting anything. You would just use the specific types you need. So if you have to have a vector V is some type of vector V, R is some type of ring R, just to get that little method to work, it's not worth it, right? Now, what about type classes? Scala has type classes can solve pretty much anything by adding extra indirection. And I don't want to knock type classes at all. I love them, and they're great, especially when you don't have any control of the original source. But the thing about type classes is they still need classes. They still need some kind of underlying model. So they're good to adapt something that you have to work with, but when you're designing something from scratch, it still just doesn't feel right, in my opinion. I think that the design isn't right. You can have these self-contained hierarchies that you then abstract over with a type class, and I think of type class as just a detached vtable pointer, whereas instead of you've just got a struct of methods effectively, and some type checking to go along with it. So let's get into how we can do better. I would propose with family polymorphism. And so if we think kind of from first principles about what are we trying to do and what are we failing to do with this abstraction, is we want to abstract over sets of values together. We want to abstract over a set of integers, or a set of floating point numbers, or a set of expressions without mixing in between. And that's kind of hard to do with traditional OO design. And so we're going to get into the kind of the code that implements this really quickly, but so the logic that goes into it is that so you have types define a set of values, right? But in Scala, values also can contain other types. And this is really key, because every stable value actually exposes an entire scope of types. And that scope of types can contain abstract types, where when you implement those abstract types, you can tighten the upper bounds, and the lower bounds of the types to which they actually refer. And this effectively reduces the set of values that scope is going to work with, handling sort of part of what we want to do there, which is work with disjoint set of values. And so every time that you have some value that's typed with an abstract type through a common path, you're actually referring to values that you know have a common upper bound, even if you don't know what that upper bound is, because you're working at it. You're working with sort of the abstract base type. But let's get into the code to make it a little clearer. So, with numbers, we'll sort of generalize just a bit to a field of numbers, or a field of elements. And so this is similar to the interface that we started out with, right? We've got a plus method and a times method, and you would also have unary minus and minus. And here's the key thing here is we have an abstract type whose upper bound is this interface here. So we're saying that an element might be something more specific than this, but it's going to at least have this set of methods, plus and times. And we'll throw in a zero there for the additive identity of the field, but you'd also have a unit value. And now let's look at how you would actually implement that. So you need to extend, you need some concrete class that implements that field element interface. So you can create a real element that takes a double. And now we need to define what that sort of abstract element is. And here we say that an element is always a real element here. And on the next slide, we'll sort of look at graphically what we're doing with the type hierarchies. And so we can implement our additive identity and a convenience constructor and our plus and times methods. And this looks kind of like the Java way with the type parameters, except that there are no type parameters around. In order to use this, and you don't need to specify type parameters. So essentially what we're doing, we have this field type, and we have an abstract type element that points and says, hey, my upper bound is this field element interface. And when we go to implement it, we're injecting the real element interface as we're tightening the upper bounds and saying, hey, in this scope, and in any abstraction that uses this scope, even if it's through a path that's typed with the generic field cape, we're always going to have this real element as an upper bound, so we can depend on its methods, which was toDouble, which was the deferred in, or I think it was value. So we've succeeded in what am I saying? We succeeded in deferring the declaration of that method into a scope where it doesn't impact other implementations, and we've kept this nice pure interface while having a still reasonable looking implementation. And another nice thing, I think it's important to keep simple things simple while making sort of these kinds of abstractions possible. And you can actually pull out the implementation of that abstract type, because we're using a static object to implement the interface. We can actually override that element type and point to this top-level real class. So you get a nice top-level type where you don't really care about abstraction. It's still easy to work with. And also notice that we're able to take advantage of Scala's value types here. So the erasure of this real type is just double when you have class members that have real members. They're just double members. There's no boxing, and there's a little overhead. These aren't inline methods, or they don't use macros, so you are doing a static dispatch to some of them, but the JVM is really good at optimizing things like that. So now, here we have something that is analogous to what you would write if you weren't giving any thought to abstraction. You just want to write some real wrapper, similar maybe to what you do with a C++ template, but you've got this object real here, which you can pass around that wraps up the entire abstraction. And so you don't get a whole lot from this, I'll admit. Before we get to the benefit really comes when you start composing abstractions without adding complexity. But I do want to just quickly sort of mention how you would use these abstractions. Well, first, you can use them, again, like you would any other type, and just want to point out again here that real has the same erasure as double, so not a whole lot of cost there. You can use dependent method types, which we'll talk more about later, to say, hey, I want to sum all the elements in some field, and you pass in, you need some common baseline for what field they're coming from, to say, hey, we're working with a common set of things here. So there is a definitely added syntax for that. There are ways around the syntax, which is one benefit over type classes, where the type classes you always have to pass in that V table, because although these will be boxed when used abstractly, we do have a V table and a this pointer, and so you actually can add these without with a method that actually just takes 2 arguments. By saying, hey, we want some singleton field, and that with singleton is important to let the compiler know that you're working with one kind of thing here. And so there's declaration overhead here, but what you end up with is a method that's as easy to call with abstract values as it is to just work with primitives. So let's look at how you would compose these things, because that's where the Java and the type parameter approach really starts to break down. So, a really important case is the idea of a vector space, where you've got some scalar field, and at some level most of the time you don't really care what that field is, right? You say, hey, I'm working with a vector space and it has some field that's consistent with itself, but I don't want to worry about that. That's an implementation detail. And so we're going to use path-dependent types here on this val scalar. And we're going to alias. So scalar is that field interface from the previous slide. And it has an abstract type called element. And we're going to define just the type alias here to make it easier to work with. So everywhere that you see scalar as a type, it's going to refer to this scalar.element, this type that's dependent on this path, which is a stable value called scalar. And so we need some actual interface that defines some methods, and say, hey, vectors are actually, we can add them together and you can multiply them by scalar, among other things. And we need another abstract type here. So we're doing the same thing that we did with fields, but we're now wrapping one of those abstractions in another abstraction. And so we've got an abstract type here. We can tighten the bounds later to provide efficient implementations. And you've got a zero vector also, like with a field. And now you can abstract over vector spaces. And admittedly, it's not, so here's a linear combination method using sort of dependent method types where you pass in a reference to the vector space first, and then all the subsequent parameters are dependent on that first parameter. Although you can take the same approach with singleton types, or projections from singleton types. And so you can do it. And let's look at an implementation of what a vector space might look like. So we want to implement R2, sort of the space of two-dimensional real vectors. And so the scalar field of that is just the real field that we defined earlier, right? And so all you have to do is define that value and assign it to the object that implemented the real field. And now we can define our vector class, and you can actually override an abstract type with a trait. You can't override traits with other traits, but you can override a type with a concrete class. So the abstract type in the interface was vector, so we can just implement that as vector here. And again, notice we're using the scalar type alias, which really refers to scalar.element. And also remember that this is a value type, so it's not boxed. This is using 16 bytes of memory to represent the vector, plus all the junky object overhead. And we can have a factory method to make vectors, our two vectors, define our zero vector, and our scalar multiplication and addition. And nice and concise, right? It's not, although you can completely abstract over this and other vector spaces that you could implement, there's not a whole lot of overhead to actually implementing one. And again, it's easy to use without, even if you don't care about abstractions. Hey, I'm doing some 2D graphics library, and I just want R2 vectors. And you can just create vectors R2. One thing I didn't point out that the factory method for the real field was marked implicit, so you can implicitly convert doubles to reals, and again, no boxing there. So you can use it nicely, just nice concise syntax, but you get the abstraction when you need it. And that's how you would call the linear combination method. And just to sort of make the case for how the benefits compound as you add capability. Because I think it is tough to make the case for abstraction. Like I said, it's not really buying you something. So let's look at what a matrix space might look like. And a matrix space is actually, it's just another form of vector space. So any matrix you can actually treat just as a vector space, and we'll give ourselves a self-type there to refer to the outer space. And like I said, because a matrix space is a vector space, we can define vector. We want to use a nicer name instead of, when we know we're working with a matrix space. So we'll make our abstract type, we'll call it matrix. It'll be bounded by some interface matrix element. And then we'll just make vector an alias for matrix. And matrices have row spaces and column spaces, right? And so here's where it starts to get interesting as we're building on these abstractions. So like with the vector space, we define the scalar field on which it depends as a value, and we use types dependent on the path of that value. So we're going to do the same. We're going to compose a row space here, and we're going to say that's another vector space. But importantly, the scalar field of the row space is the same as the scalar field of the matrix space itself. And so we use a type refinement here with, and you don't often see type refinements with this val syntax in it, but it's really handy. You say, hey, it's as if you created some custom subtype of vector space and overrode scalar to be some type, but doesn't create. This is all just type keeping, type bookkeeping. And like with the vector space, we can define row to be row.vector. So the path, so vector is that abstract type in vector space, and row is the path on which we depend, saying, hey, all the vectors in the row space come from this source. And we do the same for call. So we've got nice, concise syntax to work here for rows and columns. We've got short type names. And we can even model the transpose of a matrix space similarly, where we say we've got some transpose space, which is a different matrix space, and the row space of the transpose space is the column space of this space, ditto for the column space. And like with the row and column spaces, the scalar field of the transpose space is the same as this matrix space's scalar field. So it kind of feels like a linear algebra course, probably, to you guys out there, but we're actually able to model it concisely. This is, without heading into MATLAB or some custom system that Scala can model this really nicely out of the box, and with good performance too. So again, we'll do our type alias to sort of flatten the transpose matrix. And we'll fill in some methods for the matrix interface to multiply rows, rows and columns. And we use Scala, as some of you know, use a colon at the end of an operator indicates that it's right associative. So the multiplying the column times a row is actually a left multiplication, and it's written like that. And again, you can get the transpose of a matrix. But notice we've given nothing about, there's nothing about elements here at all. We're just working purely with rows and columns. And so what does it look like to implement this? Because admittedly, there were a lot of type incantations in that matrix space, and it's not going to be fun if you have to sort of specify these all over the place. So let's do a 2x2 real matrix space. So like with the R2 field, we just define the stable value scalar, which is the path that identifies the types of all scalars in this space. So although we're defining a val here, we're using the types within that object. And the row and the column space is a square matrix, so they're the same. And because of that, the transpose is actually just the same space. And so nothing to do there except return this. And we can implement the interface with that real field again. again, remember that value types, no boxing, nice and efficient. We'll have our factory method out there, so we can use this r2.2, treat it like a constructor. Have our zero matrix. You would also have identity in practice. And you can return the transpose. I forgot to add an actual multiplication, but you can, because we're working with R2 there for the matrix vector multiplication, you can directly access sort of that R2.x and R2.y because we're using this R2 space, we're using the paths through there, and R2 lowers the bounds of that abstract type, making available those particular methods. So without any downcasting in your code, you're able to, the Scala compiler will ensure that you're always working with the same types of vectors, the same types of column and row vectors, the same types of scalars, etc. All the compiler takes care of all those requirements and constraints so that your code can just look as simple as possible. And again, you can use this without caring about abstractions at all. And so I call this pattern kind of the cupcake pattern, where because it's essentially the cake pattern that is used in a number of Scala libraries, but it shows that the cake pattern is useful even if you have just a single type. Even in that example of a field where you bringing your interface into this scope so that you can use it dependent on these values to sort of so you get that ability to lower the type bounds and work with a particular subset of values. So just to reiterate, sort of what we did is we defined kind of this outer container for our type, and then we define an interface that declare the methods that the only ones that we want to support, no implementation details, just here's what the abstraction, here's what the interface is, and go figure out yourself how you're going to go about providing implementations. We're not going to give you any help. And the abstraction really comes not from the wrapper and not from that interface, which is a concrete trait. Even there, it's a concrete member of the sort of this cup type, even though it's an abstract class, it's a concrete member. And it's this abstract type here where we're saying, hey, here's what the bounds are. You've got some, if you're working with this pass through this value type with cup, you've got some kind of this batter material, but you don't know what it is. And it could be something more specific than what you know about. And then you declare some sort of ways to get values, although often you might get passed in instances of these types. And that's another useful thing, that these are, with sort of this pattern of having a small wrapper around a single type, you need those identity values, or you need whatever their equivalent is in some sort of convenience methods that you would put in a companion object or a static method normally. How do you get those things when you're dealing with abstractions, and we've got a natural place to put them with this pattern. And then really what I advocate is, instead of taking the cake pattern approach, and this really isn't any, you could argue that this is exactly the cake pattern, but instead of using a bunch of self-types to conglomerate a whole bunch of components into a single scope, which definitely there are times where that is necessary. As much as you can have these standalone little cakes, these little cupcakes that you compose together, it makes it easier to test. You've got something again standalone. It works better in cases where you don't always care about abstractions, and so this is kind of the pattern that we took with the vector space and matrix space, where we declared a dependency, not through a self-type, but through a value, and then possibly import some type within there just to flatten it and make it easier to work with. So that's what I call the cupcake pattern in a nutshell. And what are the consequences of this design? So the first is that we encapsulated type parameters in type paths. So we had, essentially n.matrix for some type of matrix, whereas that Java approach is, hey, with this abstraction, we have to declare all the relationships between all the types, and it's completely unwieldy. And using the cake pattern and kind of nesting abstractions this way, you can maintain a constant amount of complexity, or even as you're adding a lot of capability. And that's really what we want, right, is kind of a linear growth of complexity as we're adding capabilities, and not this sharp spike where, it's great at first, hey, we add all our convenience methods, everything that we need, and so working within our assumptions, we're golden. But as soon as you try and do something different, just the complexity explodes, and you hit a brick wall, and refactor things to death, and QA gets mad, and all kinds of fun. But the most important thing, what makes the key difference is this idea of loosely coupled interfaces with tightly coupled implementations, and that I think that this gets turned upside down with a lot of object-oriented design, because you want those loosely coupled interfaces, and that tends to lead, you can't really do it without adding a whole lot of bloat and getting stuck in that cycle of going back up to the base class, where if you have to work with every kind of a thing, then every time you have a new kind of that thing, you end up with this explosion of complexity. And that you really do want tightly coupled implementations is absolutely desirable. That's what allows you to not have to deal with, if there were no if statements there were no if it's a matrix space of doubles, there's no corner cases that you have to think about. As long as it type checks and you're not cheating the type system, you're golden. And so the tightly coupled implementations perform better too. So, although with that matrix implementation, well, you could have done it where, you could have implemented a matrix type that used some abstraction over fields, and you box everything up and use type classes. But it's about as efficient as you can get. You're going to have, you are going to box the matrices, but you're not boxing the actual values themselves, and so you don't really lose much efficiency. Except for method dispatch. And because you've got distinct types for a lot of these implementations, you end up with inline jump tables and all the other goodness that the JVM is really good at devirtualizing methods. And so these abstractions are also very friendly to the virtual machine and the optimizer. And again, what I like about kind of this cupcake pattern is one of the better OO mantras, of course, is favoring composition over inheritance. And the cake pattern tends to be a lot of inheritance, right? You end up mixing in a whole bunch of different components. And again, sometimes that is necessary, but to the extent that you can compose these things, the better. And although, as you noticed, that we had all our implementations were objects. They were top level things. And that's nice too, because you're avoiding a this pointer. When you have an inner class that's implemented in a top level object, or sorry, there's no outer pointer to the outer class. The Scala compiler optimizes that and implements it as a method that just returns the outer class. So you don't end up with that extra pointer. But there's nothing to stop you from implementing a vector space that takes as a parameter a scalar field. So, although this pattern works really nicely when you've got a fixed number of variations, and and you don't need to dynamically compose them, it's certainly possible to compose them at runtime too. So a few more reasons to like this pattern is that these cupcakes can make a nice form of enums too. And we use this at Sensity where I work, where we have to be really sure that, so there's a distinction between a data type and sort of the semantic type of thing that data holds, right? And so you might have voltage values and current values. Those are both doubles. They're the same data type, but you better be sure you're not mixing them up. And so if you kind of use this pattern where, hey, you've got sort of this abstraction of a sensor and it's got samples, instead of the traditional way would just be to use a top-level sample type with some type parameter t and maybe a string that identifies, or you take an enum as an argument, but that enum isn't part of the type signature. And so you still can get in situations where you're mixing up values, which can lead to problems. But here you can see if you want power, you want a voltage sample and a current sample, and you multiply them together, and you can't pass in voltage for current and vice versa. And you can get back the sort of sample T type if you need it. And existential type, they're not the prettiest things, but they're actually quite straightforward, especially if you work with Java's wildcard types. So they're annoying to define a little bit, but they're easy to use here. And this shows another nice thing. You can pattern matching against these sort of enum style cakes works as expected. And granted, you could do that with deconstructing a sample that takes as an argument, or some other enum that identifies the type of sample. But it's nice and readable, and it's great for reactive applications in Akka to be able to send these things around and have with very little syntax. So here we just define this one sample type, but there's a lot more potentially that goes along with the sensor. You might have buffers of sample values that you want to store in a special format, but you don't want any of your code that works with samples to have to care at all what the details of serializing those things are. So this idea of wrapping up your types in a meaningful context, and sometimes it's hard to figure out what normally when thinking about samples, some sort of sensor type is not really on your mind, and it's not always obvious what you want to wrap your types in to make them easy to work with. But if you find yourself you have some family of types that are parameterized, particularly if they're parameterized with strings or something unsafe, and you want to be really sure that it works, and that in our case that the lights don't turn out in Newark Terminal B, then having the type system back you up is helps you sleep at night. So I want to quickly contrast abstract types or abstract type members rather, with inner classes, because it is a little weird how you need these two declarations. Scala doesn't have virtual classes, which would be the analog of virtual methods, where if you want to override a method, you don't have to do anything special, right? You just declare it as non-final. But type members are not overridable like virtual methods by default, or concrete member. Traits are, as I think I say here. So if you just put a trait in another trait, it's still that cake trait is an abstract class, but it's a concrete member of that vanilla trait. And concrete members you can't override, or you can't tighten the bounds of, you can only loosen them. But when you have this incantation where you declare an abstract type with some bound, now you've actually got an abstract member. That type cake is the analog of your virtual method. And so it does need to go in these two steps to make it work. And you can see sort of the case here, there really isn't a difference. If you're only working with, the base types, you don't really, it looks like you're declaring nothing, like it's just extra verbosity, but when you want to go and extend that interface, then you see where the problems start to form, where you want to make the cake trait something more specific. Well, you can't do that. It's already defined. Everything that references sort of this vanilla swirl cake is going to refer to that base type. Whereas with the abstract type, we've tightened the bounds, so if you have a chocolate swirl cake, you've always got, that swirl batter. And a little more about path-dependent types and how they relate to. I think of them as a pretty natural extension, actually, of qualified names. So you've got your typical package with a class, and so that's your normal, ordinary qualified name, which you can import, etc. But if you've got a type inside a trait, you have to use this hash. You have to use a type projection, which is this hash operator here, saying I want to reach inside and get the type out of that trait. Now, classes nested inside static objects are just ordinary top-level classes. They're just syntactically scoped. And so you can just use that foo.bar like a normal qualified name. But the type is actually a type projection on the singleton type of the object. So that's internally what the compiler treats this foo.bar as. And where it gets, where Scala really gets unique is with these stable immutable values. And I remember when I first learned Scala, looking at vals and being like, oh hey, that's just a way to stop you from updating a variable. But vals are really much, much more than that. They're not just a variable that you can't update. And the key reason for that has to do with path-dependent types, that this value here, although it's not bound, it is a source of all, it has all the types, it's got path-dependent types relative to it. And if it was a var, then the compiler couldn't prove that types or values typed with dependent types through that value aren't changing because you can reassign the var. So I think of path-dependent types like qualified names, where you can substitute in different implementations depending on the context that you're in. And you can import them just like you can, if you have a value, you can import the type members of it just like you would a qualified name. And each unique path kind of overlays this unique set of types, which again is what gives you that nice scoping, that where you're working with a fixed subset of values with that base type. And dependent method types and singleton types are so if we're saying that all the types that you're working with are dependent on some value, well, how do you use them in some other scope? And the answer is with dependent methods types and singleton types, which until recently were incredibly buggy and would crash the compiler all the time, but since Scala 2.10, they're mature and they work nicely. And so let's talk about scary existential type projections, which the Scala compiler now warns you away from, makes you import some annoying language thing to even use, which I think is silly. So the first thing to note is that here, I'll go show the next line. So how do we refer to sort of that inner type there? And we said on the previous slide that you can do cup, hash, cake, but I want to show just the equivalence of, for thinking about existential types in a simple context, that we're really, the way you express that simple constraint is, well, you've got C for some type, C is some kind of cup. You're just saying, hey, I've got some type of cup, and that's just like a normal type down, in a really stupid way to put it. But it's useful for thinking in the simple case for when it gets more complicated. And so, to refer to that inner type, you say, hey, I've got some type of cup, and then you take a type projection from that existential type. You're essentially saying, I have some type of thing, I don't know what it is, and I don't care, but I want some type out of it. But again, you should never use existential types for this case. You can just use the type projection of the top level thing. But there are cases where you do need the existential type, so it's worth considering the simple case first. So what if your outer type has some type parameter? Like with that sensor example, the outer type had a type parameter t. And that's another thing worth noting about why I like this sort of cupcake pattern for wrapping up in noon type style things is when there are arguments for voltage.sample and current.sample, you didn't see double anywhere in there. There were types, the path abstracted over those type parameters. And you can do that for, like with the matrix space, you're abstracting over type members, and you can abstract over type parameters too, and you can bundle them all up so you don't need to keep reiterating all of these type bounds every time you declare a method. So how do you refer to sort of the cake inside that cup T? If you try and do the preferred approach up there, the compiler's going to complain and say, hey, you want a cake of some, a cup with some parameter? Well, I don't know what that wildcard type is, and I give up. So here's where you do need the existential type. So like up there, we say, hey, we've got a cup of some kind of type parameter, and now the wildcard type can exist there. You've got some kind of thing with some bound, and you want to get the cake out of it. And a little bit about type refinements, which we saw in the matrix space example. If you want to say, hey, a lot of time, ideally, we want to be able to specify constraints when we care and not have to worry about it when we don't care, right? And that's one of the downsides of the type parameters approach, is you always have to specify them. Even when you just want the default constraint, specify the type, too bad. Every method that uses them generically has to specify each one of these types. And type refinements are preferable because you declare them when you want them and you ignore them when you don't care that they exist. And so it's just a simple example saying, hey, you want a box of chocolates, you got a box and you specify the value, or if you have an abstract type, you can use the type syntax for type refinements too. And then just to reiterate a little about the dependent method and singleton types, and this is sort of the nastiness that, I don't think it's particularly nasty, but it sort of looks crafty until you see what it buys you. And I think, seeing how you can keep implementations kind of orthogonal and how you can nicely abstract over things, in my opinion, really justifies the type funkiness that you have to go through. And it's really what you want. You want to tell the compiler what the constraints are so it can help you out. And so you need to specify that some way. And so, it's important to note that for dependent method types, you need separate argument lists for where you're passing in the path that you want, that your types are dependent on, and then the arguments with the types that are dependent on that path. And so here, the cake parameter specifies a cake that comes from that cup parameter in the first argument list. The compiler is going to complain if, I forgot to underline it. The compiler will complain with that second one there. And then sort of the particularly not pretty syntax for using these type projections of singleton types, where you're saying, hey, I don't want to make the kind of consumers of my library have to pass in this, this object every time, for this particular method that's maybe called a lot. You can have a type parameter with the singleton type of the path. You're saying essentially that you don't want a group of types, you want some specific type, and then all the values are going to come from the same place, and that makes sure that it's sound. And if you try and do it, if you try and omit this with singleton here, there's no way to know that you didn't pass in, you're not passing in cakes from sort of these two different outer types, and so it wouldn't be sound. So that's for button. So, in summary, kind of Scala's type system, definitely, particularly the outer edges of it, that I really don't see used a whole lot. And my presumption is that people don't really see the value, or it's difficult to find ways to take advantage of it. But it allows you to do things that you really can't do in other languages, or you wouldn't dare do. In a dynamically typed language, you wouldn't ever presume that, if you have some addition method, that you're going to get two objects of the same specific thing. You wouldn't dare. So you add a whole bunch of expensive guards, if it's this, and a whole bunch of dependent types are much better than dependent behavior. As much as, maybe, it'd be nice not to have to specify this sometimes. You can structure things so that the type overhead is low, and what you gain from not having to support effectively undesired behavior, and where it's just wrong, you can make it invalid to use your types in a certain way that allows you to simplify assumptions, simplify your code, and really make it clear and perform nicely. And I've never seen another language that can do this quite as nicely as Scala. And again, a bit of a simple example with numbers, but everybody here is building pretty complex systems, and I think that we really need tooling to help us do a better job at reducing the footprint of kind of these complex interacting systems, and I think that Scala or something like it really is that tool, and I hope people take advantage of it and really put it to use it to its full potential, and so you don't lose out the argument with the Java folks who see, hey, who see Scala as, hey, okay, it's great that you've got type inference and stuff, but think that it doesn't really buy you much. And I think it buys you a lot. Like I said, I'm sure a lot of people who work on, cloud software, etc., who, we're obsessed with linear scalability of our systems. And yet we don't have that, I would argue, with a lot of the software frameworks that, we build those systems with. You have very nonlinear scalability of abstractions and components, and Scala deserves, the name was chosen well as Scala, the scalable language, and we should use it, take advantage. All right, thanks a lot. So